So this webinar is organized as part of this project called the Arctic Black Carbon Impacting Climate and Air Pollution, so ABC-iCAP. It's an EU-funded project, and it's this kind of collaboration project of knowledge sharing, awareness raising, and with some expert analysis included to be performed with some stakeholders important, especially for the EU. So notably some non-EU Arctic countries, as well as relevant international organizations. Here's our schedule for the day. And without further ado, I will present the first speakers who are coming from the Finnish Meteorological Institute. So Xiaoxia Shang, Antti Lipponen, and Tero Mielonen, who are going to talk about remote sensing capabilities for observation of wildfire smoke plumes in Finland. I will stop sharing and hand off everything to you. Go ahead.
Thank you. All right. So on this map, you see all the fires from the last summer occurring in the summer season. So all these markers show a wildfire that occurred between 1st of June and 30th of September this year. So as you can see here in Finland, we don't have too many big fires, or either in Scandinavia. So this happened last summer, and this is normally the case. We don't usually have large wildfires here in Scandinavia, but we often get some smoke transported from some fires further away, and therefore we need capabilities for monitor the wildfires. On this slide, here is one case from last summer. So in August, there were large wildfires in Russia, about 400 kilometers east of Moscow, and roughly about 1,200 kilometers from Kuopio, our hometown in eastern Finland. So on the bottom right here, you see satellite images for one day for these fires. And these satellites are useful in fire monitoring. As seen from the previous slide already, the satellites can detect both the active fires and also the smoke produced by the fire. And we can use this satellite data to monitor the smoke transport in the atmosphere. Here in Finland, we don't have own satellites to use, so we often use European and American satellite data. On the left here, you can see model trajectories that show the air masses. Do you all see the second slide already, or do I? Good. So on the left, you see the model trajectories that show where the air masses were coming from to Kuopio, along with the winds on August 19th. So here you clearly see that the air masses were arriving here from the location of the fire, and it took about 72 hours for the smoke to arrive here in Kuopio. Here up right, you can see the observations of an instrument called a sun photometer located in Kuopio. So during the day, sun photometers are looking at the sun every 5 to 15 minutes, and in cloud-free conditions, they give us accurate information about atmospheric aerosols such as smoke. And in this case, the quantity this sun photometer was producing was the aerosol optical depth, which was quite high, about 0.4 measured at 500 nanometers. Typically, these values in Kuopio are below 0.15, so it was quite high values, so there clearly was some smoke in the air. We have 5 of these sun photometers in Finland that belong to NASA's Aeronet observation network, and they give accurate information about the atmospheric aerosols, so they are a useful tool as well to monitor the smoke. And then Tero can take over.
Yes, so my role in this presentation is to show how our unit got involved in studying smoke plumes in the first place. And it all started during the warm summer of 2010. Russia had huge wildfires like most summers, but this time we had the chance to smell them as well. And this satellite image here from the 8th of August shows the plume extends over 1,000 kilometers and reaches the eastern part of Finland. The plume was so thick in the middle that the MODIS aerosol retrieval considered it to be a cloud. So there was quite a lot of smoke on the move. And then here in the smaller figures, you can see the trajectories of the plume, and it clearly shows that the like what the previous image showed, that the plume was reaching this going west or northwest. And then they have in the middle you have the aerosol load from the MODIS satellite, this AOD that Antti already mentioned. And then there's this carbon monoxide, which is a good tracer for wildfire smoke. As you can see when you compare it with the satellite image, the shapes are quite similar. But Kuopio wasn't the only place in Finland to be affected by these plumes. They were also observed in Sodankylä, which is in the northern Finland. And this figure shows the time series of aerosol load in Sodankylä observed with 3 different instruments. The smoke plume hit Sodankylä in the end of July, and which is in the middle of the plot, and it's quite easy to see from when comparing with the other values. So this just underlines the impact of these plumes can have on air quality in Finland. And then this figure shows the observations of aerosol size distributions done in Kuopio during summer 2010. The gray line shows the normal days, and then the thick black line shows the smoke event. In addition to the increased number of aerosols, also their size increases when there's smoke present, and then we have a larger masses of aerosols. And then as the last figure, here's an example of the modeling studies we have done. We used a chemical transport model to study the evolution of the plume and noticed an interesting feature in the aerosol composition. So on the left, you see over Moscow the aerosol composition, and half of the aerosol mass comes from the primary organic aerosol and black carbon. But over Kuopio, the fraction of these primary aerosols is only about 15%. Most of the aerosol mass had formed during the transport from the organic gases in the plume. So the composition had changed quite a bit. And that, of course, affects all the other properties of the aerosols. We didn't have LiDARs in 2010, so we didn't get this detailed vertical information on these plumes. But we have LiDARs now, and Xiaoxia will tell us what kind of neat things we can get out of them.
So now, first, I will shortly introduce you our instrument. LiDAR is the short name of light detection and ranging. Here is the principle. The laser pulse are emitted into the atmosphere, which can be absorbed or scattered upon interaction with molecules or aerosol particles. The radiation to the backward direction can be then captured by the instrument. Using this detected signal, the vertical distribution of the atmospheric aerosols can be estimated using the time between the emission and the reception of the time. Aerosol properties can be evaluated using LiDAR-derived parameters. In FMI Kuopio, we have this multiple wavelength Raman polarization LiDAR polyXT. Here is the photo of polyXT and some instrumental details. There are several ground-based LiDAR networks available among the world with hundreds of advanced LiDAR systems, for example, EarlyNet over Europe and PLNet over United States. Besides these LiDAR stations, many national weather services has built up these ceilometer networks. For example, on the top right, I show you a map of FMI's ceilometer network. Ceilometers are typically the single wavelength backscatter LiDAR operating in the near infrared. Even though ceilometers were originally designed for the detection of the cloud height, ceilometer measurement has been used in several aerosol studies. In our measurement site, we also have 2 ceilometer instruments really close to the polyXT LiDAR. The information provided to this large number of ceilometers can fill the gap between the advanced LiDAR stations. Besides these ground-based LiDAR stations, we also have spaceborne LiDARs, which can provide additional information at the global scale of the aerosol and cloud. Studies have shown that it's possible to estimate the mass concentration using LiDAR-derived backscatter coefficient. Actually, both advanced LiDAR instrument and ceilometer can provide the aerosol backscatter coefficient with quite high accuracy. However, the accuracy of aerosol extinction coefficient is really sensitive to the estimate of the unknown LiDAR ratio. LiDAR ratio is an aerosol type dependent parameter. Its typical values for several aerosol types is available from the literature. It's also possible to estimate this value from measurement. Then, using the aerosol extinction coefficient, we can estimate the volume concentration using this extinction to volume factor. Some statistic values of this factor is available for certain aerosol types from the literature, for example, for smoke, dust particles. It's also possible to calculate this factor using the aeronet inversion product under some conditions. And finally, from the volume concentration and this particle density, we can calculate the concentration, mass concentration. And now I'm going to present to you a case example using the ground-based observations over Kuopio, Finland. Here I give you the time height color plot of the poly-XT LiDAR observations. The color is related to the intensity of the backscatter LiDAR signal, which is refers to the amount of the aerosol in the atmosphere. For example, here inside the boundary layer below 2 km, we can observe some enhanced values, and this could probably due to the presence of high load of pollen on that day. A quite thick pronounced lofted layer can be easily identified here with red color, located at about 5 km in the morning, descending to about 2 km in the evening. We have performed this back trajectory analysis to study the air mass. Results show that the particles inside this lofted layer has traveled about 7 days from forest fire sources in Western Canada. Next, for further analysis, we have derived the vertical profile backscatter coefficient using the 2-hour time averaged LiDAR profile. Here is the result at 3 wavelengths of poly-XT LiDAR and 1 wavelength of ceilometer. After applying the methodology I just presented, we have estimated the vertical profile of mass concentration independently using the backscatter coefficient at each wavelength. We can find quite good agreement on the estimation of mass concentration from poly-XT LiDAR and ceilometer, showing the potential of using ceilometer to estimate the mass concentration. We have also compared these LiDAR observations with the MIRA-2 model data. You can see for the early cases, MIRA-2 seems to show a little bit lower mass concentration. However, for afternoon cases, MIRA-2 shows a little bit higher mass concentration compared to the LiDAR observation. However, we should notice that both simulation and observations has non-negligible uncertainties, and regarding this uncertainty, the result still shows quite agreement, especially for the altitude of this layer height. So these are from the ground-based observation. We can also study the aerosol using spaceborne observations. Here, we are going to show you case examples using the spaceborne LiDAR Calliope on board the Calypso. We selected 2 Calypso tracks, one on the 3rd of June over United States, and the second on the 7th of June over Europe. We want to compare the spaceborne observation with the ground-based observation, thus we selected 2 stations, one LiDAR station from MPLNet and 1 ceilometer station from ALICE-net. We have found that during this period, there were clearly intense forest fire events occurred inside this fire area. As you may know that Calypso can provide the aerosol typing product. So for these 2 selected tracks, I plot the Calypso typing provided by the Calypso here. Types are showing by different colors. In this study, we are interested in the elevated smoke showing in black. For the selected tracks, we can see several smoke layers detected by the Calypso. So using trajectory study, we can analyze the air mass, and for this example trajectory, we find out that this smoke layer over Europe and this smoke layer over United States are really coming from the same source region where there were wildfire. And now I'm going to show you some more in-depth analysis of these two smoke layers. Again, I put the color plot of these two tracks here. So for the smoke layer from the first track, we have do some small time averaging of the Calypso backscatter. We see the Calypso backscatter at 64 is quite noisy in red, but the one at 532 looks quite good. And in this study, we only use Calypso backscatter at 532 to estimate the mass concentration. In order to compare with the ground LiDAR, we also plot the backscatter from the ground LiDAR here. You see both LiDARs identify quite well these three aerosol layers. And after the methodology, we evaluate these vertical profile mass concentrations. It seems a little bit discrepancy were observed between the space bomb and ground-based LiDAR. However, regarding the uncertainty, the result is still quite good, consistent. Similar analyses were performed for the second layer from the second track, and the result is showing here. We see that a much better agreement was found here from both space bomb and ground-based observations. And now if we want to compare this layer quite close to the fire source region and the second layer, which is really far from the source region, we can see the altitude of the smoke layer decrease a bit. However, the depth keeps quite well the same. And regarding the mass concentration, quite similar value were found for both smoke layer, which means even after 4 days long-range transportation, there are still similar amount of smoke particles there inside these lofty layers. Now I leave Tero for the conclusion.
So just to conclude, even though we don't have huge fires in Finland, we are still interested in studying and monitoring them because smoke can be transported here from the other parts of the boreal region. And by combining these in situ and remote sensing observations with modeling tools, we can get pretty good understanding of the properties of these plumes and their evolution. So if you got interested in our results and tools, we are happy to collaborate. Feel free to contact us. Thanks.
Yeah, thank you. That was excellent. I'm gonna give it an applause reaction. But I think that was so great. I have to say that was the best explanation of Calypso and Calliope I have ever seen. So congratulations on that. Like, it is a very difficult instrument to understand. So at this moment, we do have just a few minutes to go over Q&A. So I'm gonna open up the document. Let's see. Anonymous Cheetah is starting to finish up a question here that I think is good. Are there any expectations that wildfires in Finland will increase in the future based on climate change related impacts on fire regimes? And by that way, smoke too. So smoke impacts as well. Has your group looked into that?
I think there have been this kind of analysis for the future scenarios, and at least the potential for these fires increases also in Finland. But then, yeah, if we keep raking our forests, then we will be safe. But I'm guessing that,
yes.
I'm guessing that we will also, because also like in Sweden, there were this kind of a few years ago, there were these big fires. So
yeah,
I would fear that there will be more fires also in Finland.
Yeah, and it does seem like your location also means you could have more impact from smoke from other nearby or even long range fire regimes increasing. So I wrote a really long question, but have different LiDAR or celiometer networks across the international science community ever worked together to track extreme smoke events real time? Because I mean, this is really great capabilities that you're showing from your group in Kuopio. But as you're doing this, have you ever coordinated with, say, a Canadian group or other EU groups or European groups so that you're exchanging data real time?
Actually, for this study, we have cooperation with this Italian group of the AliceNet and also the vertical profile of the backscatter, we didn't retrieve them. It was the MPLNet, the personnel from this MPLNet provided the data, and also the profile is available online, I think. And as we know, we have large number of centimeters, and actually the centimeter raw measurement is also available online for this example, the e-profile.
Yeah, yeah.
As for our polyXT, the raw LiDAR profiles, the quick looks is also available in near real time online from this Polynet website. Just, I would say for the level 1 data, the observations are almost near real time online available and mostly free access, I think. But for the level 2 data, which means the vertical profile of aerosol properties, we may need to ask the person to have the data.
Yeah, that's really interesting. Another question, I don't know if you all have tried to do this, but can the LiDAR or celiometer networks then detect smoke impacts from smoldering fires in the winter? And I think they're talking about maybe like overwintering fires. Have you ever looked at those types of smoldering fires? I guess they would have to actually create enough smoke, right? They would create CO, but as you said, that's a great marker for wildfire. But that CO is mainly from satellite products. Is that correct? Okay. Excellent.
Yeah, of course, there's also CO observations, in situ observation, but then you like have few of them scattered all around.
Yeah, it's just individual sensors, right? Not like a whole network. Yeah.
Yeah.
So I'm gonna finish with this question, and feel free to say you don't rake your forest, but this forest management is not necessarily removing always the grounds layer. Or should we ask a forestry group in Finland that question? So I think the question is more
maybe
about
the forestry
fire
people
risk.
know how to answer that better.
Yes. Okay. Well, I want to thank you, Xiaoxia, Antti, and Tero so much. I really enjoyed this talk.